This is the video for Westlake Chem 1's lecture over intermolecular forces. First off, I've got to do a little bit of definition here. Intermolecular forces versus intramolecular forces. That prefix, inter versus intra, is a very distinct and important difference. We need to clarify that before we talk about any kind of intermolecular force, or IMF. An intramolecular force is any kind of force that exists within the molecule. So for us, that means bonds. Ionic, covalent, metallic, those are all forces that exist within the molecule itself to help hold the molecule itself together. So any kind of force that holds the atoms together to give you one coherent molecule. As opposed to an intramolecular force, intermolecular forces are any set of forces that hold multiple molecules together. So, for example, an intramolecular force are the bonds that hold your H2O together. It's the H and the O bond. Whereas an intermolecular force is the force that holds each H2O to the other H2Os. These intermolecular forces are technically weaker than any kind of true bond. They are still very, very important when it comes to determining the properties that different molecular compounds have. So why does water boil at 100 degrees and not higher or lower? Well, that comes down to intermolecular forces. We've talked in the past about the fact that covalent compounds can be solids, they can be liquids, they can be gases at room temperature. We said, it's really hard to predict what the properties are going to be just from the looking at the structure, looking at the formula. Well, these are why. This idea of intermolecular forces are the leading determining cause of what is your boiling point, what is your melting point. Is it aromatic? Is it solid? All of these kinds of things are all determined by intermolecular forces. So in order to determine what state of matter a covalent substance will be, we would essentially have to look at the strength of the IMF. We have three phases, solid, liquid, or gas. Maybe you can use a little bit of logic to kind of tell yourself that, hey, if my covalent compound is a solid at room temperature, that's probably going to be some strong intermolecular forces. These strong forces hold your molecules together tight enough that it is a solid, tight and rigid with a set structure, and it takes up a minimal amount of space. Liquid is always kind of the middle child. It has medium space, so medium volume, and is a little fluid but still has a set volume. Versus your gases are going to be your weakest IMF because there's very little interaction between the gas particles themselves. So we can tell a little bit of something about the strength of the IMF versus what state it would likely be at room temperature. We will never make you predict what phase something would be from an IMF, but we might give you two compounds and say something like, this is a solid at room temperature, this is a gas at room temperature. What does that tell you about the IMFs? Well, then you can tell a little something from that. So there's three kinds of intermolecular forces, just like there's multiple kinds of bonds, multiple kinds of intermolecular forces. I'm going to refer to intermolecular forces as IMFs from here on out. That's just our speed shorthand abbreviation. So IMFs stand for intermolecular forces. Anyway, three kinds of IMFs: dispersion forces, also called London forces, dipole dipole interactions, and finally hydrogen bonding, which is a little deceptive. But first, let's talk about dispersion forces. So dispersion forces are the weakest of all the intermolecular forces. Every single covalent molecule will exhibit dispersion forces. They are just these random spot of the moment forces that exist because maybe for just the briefest moment in time, more electrons are on one side of your molecule than the other. If you have an overall nonpolar molecule, which we learned about last time when we started talking about polarity molecules, the only IMFs that those molecules will experience are dispersion forces. This is a visual to kind of help you maybe try to understand this idea of dispersion forces a little bit better. At the very beginning of time, you have two atoms, atom A and atom B, and they are perfectly symmetrical. They are nonpolar molecules, no overall charge one way or another. Remember, electrons are constantly moving, though, so maybe you let the molecule sit for a little while and then you stop time, and the moment you stop time, one of those molecules just happens to have more electrons on one side of the other. So atom A would have a few more electrons over on the right, giving it a negative charge. A few less electrons on the left, gives it a positive charge. And again, that's just based on this random movement of electrons constantly going. And because one of your molecules has a positive and a negative, it's going to cause another atom next to it to have a positive or negative because, again, opposites attract, but more importantly, the same charges will repel. So if the right side of my molecule has a bunch of negatives, it's going to force the electrons on another molecule near it to push its electrons farther away. So it's going to induce this charge. And it's going to make every other molecule nearby copy it. In that very brief moment in time, remember we froze time, in that moment that we've frozen, that is the charge that this thing has. But the moment you start time again, maybe it goes back to as it started. It redistributes its electrons, it's even again, it's back to neutral. You let it sit again, you pause time, well now maybe it's flipped. Now maybe there's more electrons on the left side than there is the right side, and you'd get a situation kind of like C down there, where this time I have more electrons on the left. Well, because they're on the left, and you have a positive side on the right, it's going to attract some electrons from the atom next to it, causing the atoms around, or the molecules around it, to start copying the charge, so it's negative on the left and positive on the right. Again, we call this an induced dipole. It's a very temporary charge brought on by the molecules around it. It is very, very weak. It is very, very temporary. Again, the moment you restart time, they balance each other back out again. Everyone goes back to neutral, and you don't have any connection. It's these positive and negatives that are creating an attraction between the molecules themselves. Dipole-dipole interaction, being the weakest, is pretty representative of what we see with gases. There is not a whole lot of interaction between gases, but there are moments when there's some attraction. That moments of attraction are caused by these induced temporary dipoles. The way we can kind of rank strength of various things with dipole forces, just rule of thumb, the more mass something has, typically the more electrons it has, because the more mass comes from bigger and heavier atoms. So more mass means more electrons flying around. More electrons flying around means in those moments where one side has more electrons than the other, there's a higher chance that there's more electrons on the left than there is the right. So you have these potentially stronger dispersion forces. If that's confusing, don't really worry about it. Just put it in your head that the bigger the molecule, the stronger the dispersion forces. That's all you need to worry about. This idea of the bigger the molecule, the stronger the dispersion forces is very easily illustrated using the halogen group. So fluorine and chlorine, the smallest of the hydrogens, are gases because they have very, very weak IMFs at room temperature. Bromine, though, is a liquid at room temperature. Because it's a little bit bigger, because it's a little heavier, because it has more electrons, it has slightly stronger IMFs. When you look down at the next two halogens, iodine and AT, those are going to be solid at room temperature. Because iodine and astatine are bigger, they have more electrons, but the difference between I and AT and bromine, Br, is, well, they're bigger. They have more electrons because they have more electrons and more mass. They can have bigger IMFs because they have bigger and stronger IMFs. they can hold on to other iodines or other astatines a little bit better, which will allow it to be a solid at room temperature. So again, you can see this difference between the stronger your IMF, the more likely you are to be a solid or a liquid versus just a gas. So that's everything about dispersion forces. Everything has them, and they're very temporary and tend to be very weak. Next up is dipole dipole. They're pretty similar to dispersion. The difference is dispersion is a temporary dipole. Dipole dipole is a permanent dipole. So when you have two polar molecules that are attracted to each other, all that big old paragraph says is that the positive side of one molecule is going to be attracted to the negative side of another molecule. And you get these big old daisy chains where a plus is attached to a minus on one guy, and that same guy's plus is attached to another negative, and that negative is attached to another positive, and that positive is attached to negative, and you get this big old chain of intermolecular force holding large groups of molecules together. Polar molecules have both dispersion and dipole dipole, but dipole dipole is so much stronger that we get to ignore any kind of contributions made by the dispersion forces. So yes, a polar molecule is going to have both dispersion and dipole dipole, but because dipole dipole is so much stronger, we get to just ignore dispersion forces. So when we ask you, hey, what kind of IMF would this molecule have, we'll always expect you to just tell us the strongest that molecule has. Here's kind of a visual representation of that dipole dipole. I have HCl, a polar molecule. There's more electrons on the Cl side of my HCl, which means when I look at my HCl molecule, my hydrochloric acid, my H is slightly positive, my Cl is slightly negative. It's going to go find another HCl, and it's going to create this little attraction between the Cl of one HCl and the H of another HCl. It's not a true bond, but you get this attraction between positive and negative. And maybe then it starts floating away from each other. Well, it's going to go find another HCl. It's going to find another HCl and make another temporary or another bond that's caused by these permanent plus and minus. That HCl will always have a positive H and a negative Cl. That's just based on the way the molecule is created. It's based on the electronegativity. Cl is going to be better at attracting electrons within the bond, but also all those extra electrons just hanging around the Cl makes my one side of my molecule more negative. Permanently will make my Cl more negative. H will never be able to be negative. H is always going to be positive because it's always going to have less electrons near it. So this permanent dipole creates a stronger attraction than my dispersion forces. Last but not least is hydrogen bonding. It's deceptive. It's not a true bond. It's just called hydrogen bonds because they are so much stronger than dipole dipole. They almost start to imitate bonds. Hydrogen bonds are exactly the same as dipole dipole. They're just dipole dipole bonds on steroids. They are super strong dipole dipole bonds, so much stronger than other dipole dipoles that it became its own category. They are formed when you have a dipole dipole interaction, specifically between H and either N, O, or F. You have to have an existing bond between H and O, H and N, or H and F in order to have a hydrogen bond. So when you're looking at your molecule, you have to be very, very careful to make sure that you have an existing bond between HN, HO, or HF before you can say, oh yes, this is in fact hydrogen bonding. Here's a couple examples. Water is a very, very good example of hydrogen bonding. You have that HO bond right there. You have another HO right there. The reason hydrogen bonds are so strong is because that difference in charge, the plus from your hydrogen and your minus on your minus from the electrons on the oxygen, is so drastically different that it's going to be able to create this really, 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 really strong attraction between the H and the other O. Water's really special. It can make up to 2 hydrogen bonds. We can give you more details about that in class. But for right now, really remember that we are looking for those F, H, O, H, or N, H bonds. These 3 are what make H bonding a thing. Okay, so you have to have an example of that in here. When I look over at this other molecule that we have, H3COH, we have that OH bond that exists within the molecule, and that drastic difference in charge is going to allow us to go find another drastic difference in charge and create this temporary attraction between the H and the O. It's a very, very, very strong attraction because you have a very, very strong difference in plus and minus charge. Don't worry too much about this graph. It's just another kind of visual to kind of help you try to understand these relative strengths. If I look at the bottom line, that's a bunch of nonpolar molecules. Remember, nonpolar molecules only have dispersion forces, so they have the weakest forces holding them together, so they have the lowest boiling points. As I start getting bigger, H2S, HCl, pH3, those are all polar things, but they're not hydrogen bonded things. So even though they do have stronger forces than all my nonpolar molecules, dipole dipole, they're not quite as strong as those 3 that we have on the left, H2O, HF, and H3. Those are my hydrogen bonding molecules. Their IMFs are so much stronger, they tell us that we have a much, much bigger boiling point for their size. Remember, H2O only weighs about 18 versus H2TE and antimony trihydride and hydroiodic acid all having weights of like 130 over here. Even though they're so much bigger, they're not really able to compete with water. And it comes down to the strength of the IMS. Even though it's a much smaller molecule, that hydrogen bonding is just so dramatically stronger than any kind of dipole-dipole that our other polar molecules would be able to put up. If this graph confuses you, don't worry about it. It's just another way to kind of help you visualize these strengths. Dispersion is the weakest, dipole in the middle, hydrogen bonding at the top. Here's some more representation. We're never going to throw 3D molecules at you, but if you ever have to take chemistry in college, it's really starting to become pretty common to look at 3-dimensional molecules. Here we have an example of hydrogen bonding between methanol and H2O. You have an OH bond right there. That's what the red molecule is oxygen, and the blue is hydrogen. So I have an OH bond there. I have another OH bond there, which is going to give me some hydrogen bonding. If we look to the right, we have a methanol molecule, again, CH3OH, so it does have that OH bond, which gives us the potential to make a hydrogen bond. But when it goes to find a partner, it's going to be partnered with chloroform. Well, chloroform doesn't have one of those 3 special bonds, HF, HO, or HN. It has HC. Well, that's not any of those. So because chloroform doesn't have one of those 3 special bonds, it can't make hydrogen bonds with my methanol, which means, well, if I can't have the strongest hydrogen bonding, but both of those are still polar molecules, now my strongest is going to be dipole-dipole. When I look at the bottom, I have 2 nonpolar molecules, 2 hydrocarbons, CH18 and C6H14. So octane and, I think that's hexane. No, it's not hexane. Yeah, it is. It's hexane. two nonpolar molecules. Nonpolar molecules can only ever have a London dispersion, or just at this point we just call them dispersion forces holding them together. So remember, polar are going to be either H bond or dipole dipole. Nonpolar will always just be dispersion. So here's a few examples. SO3. You can do your NASAling, get your structure, draw it out. I have our example right there, already done. First, before I can answer the IMF type, I have to figure out whether I'm dealing with a polar or non-polar molecule. Well, with SO3, I start with my first question. Does my center atom have lone pairs? It doesn't. So then I move to the next question. Is everything around it the same? Yeah, O, O, and O, which means SO3 is a nonpolar molecule as far as we're concerned. Because it's nonpolar, the best IMF it can give us is going to be dispersion. So we have to identify polarity first, then we can deal with IMF. Br2, again, a nonpolar molecule because it's an even distribution of electron, which means the best we can do is dispersion. Again, being able to identify that polarity is crucial in order to figure out IMF. CF2Cl2, well, first thing, does my center atom have lone pairs? No. Is everything around it the same? No. So that tells me that this is going to be a polar molecule. Now, it can either be dipole-dipole or hydrogen bond. You have to determine which one it is. Well, remember, if it's hydrogen bond, I have to have one of those either HF, HO, or HN bonds. And when I look at CFCl2, there's no H's in there. So there's no way it can be hydrogen bond, which means process of elimination tells me that it's going to be dipole-dipole. When I look at HF, HF is going to be polar. You see that uneven distribution of electrons. I have more electrons on the left than I have on the right. So HF is definitely going to be polar. Then I have to look and see if I have one of those three special bonds. Well, HF is one of those three special bonds. So it will have dispersion, and it's going to have hydrogen bonding because it's going to have that extreme dipole-dipole interaction because it has that HF bond. It's going to find other hydrofluoric acid, and it's going to make that really, really strong attraction. SCl2, first question, does it have lone pairs on the center atom? It does, so I know that this is a polar molecule. And because it's polar, that tells me it's either going to be dipole-dipole or hydrogen bond. There's no hydrogen there, so it has to be dipole-dipole. All right, that's really it. That's as quick as it is. If you can identify a polarity, you can pretty quickly identify IMF type. Make sure you're getting your practice in, make sure you get your homework done, and if you're still kind of lost, how do I connect IMFs to polarity, or how do I know which of the three to even start with, or I'm still working on getting that polarity down, please come see us so we can work through some examples with you, and we'll get it down so that you could basically do this in your sleep.